Hello students, this is Kashima Soni and today we are going to start our new topic, that is Valence Bond theory for coordinate complexes. Correct, so we are basically going to see the postulates related to the same in this very video. Alright, so proceeding to the introductory portion. VBT, that is valence bond theory, was developed by the scientist named Linus Pauling, correct? And his main assumption was that ligand donate an electron pair to the metal and it result in the formation of coordinate bond between these two. What am I saying? Metal having empty orbital, ligand donates its lone pair of electron in this empty orbital of metal and it will result in the formation of a coordinate bond, coordinate covalent bond, something like this. Correct. So yeah, proceeding further, we have categorized ligands into three parts. First is your strong, second is your average field ligand, and third will be weak field ligand. So let's take up each of them one by one. First, we will talk about strong field ligand. They are actually good, very good electron donor, and they will pair the unpaired electron in your central metal atom. By that, what I mean is, for example, this is the d orbital of your metal, and it is having 4 unpaired electrons. What will be your strong ligand like cyanide will do? It will pair these two electrons like that. Okay, and it will result in the pairing of unpaired electron. Correct. So this is about your strong field ligand. Proceeding to the average field ligand, which act as an intermediate between strong and weak field ligands. As I told you, it can act as both weak and strong field ligand and their average electron donor. So these are the examples of the same: NO2 negative, ethylene diamine, En, H2O, water, ammonia, EDTA4 negative, then SCN negative and OH negative. Most of them actually going to act as a strong field ligand, correct? And next is, yeah, so here comes the note. You have to keep that in mind, that whenever your lesser electronegative atom is present, it would be your better donor. As mentioned, lesser electronegative, good donor it will be. So you know, carbon as compared to oxygen is very less electronegative, which is why it is going to be good donor. Okay. So next we have weak field ligand. As I told you, it is going to be poor electron donor and it will not going to pair unpaired electrons, and all the halogens will fall into this category: SCN negative, where N is going to be your donor atom, and S2 negative are the example of the same. So what are the properties basically of your VBT? You are going to study basically hybridization. You are going to know about the hybridization, magnetic moment you can calculate, spin multiplicity you can check, and magnetic nature as well. Proceeding further, there comes the postulates of VBT. So the very first theory postulate of the same, as I told you, it is developed by Linus Pauling and it is based upon some following assumption. The first assumption would be your central metal atom. It makes available number of vacant s, p or d orbital equal to its coordination number to form covalent bond with orbitals on the ligand, which they mean that if we are having four, over here we have 4 coordination number, correct? So your metal should have at least 4 vacant orbital, so that your ligand can donate those electron to the 4 vacant orbitals of metal, correct? So this is what has been mentioned in your first postulate. Alright, so second postulate says, since the maximum angular overlap of 2 orbitals forms the strongest bond. What they are saying, that maximum angular overlap, it will result in the formation of a strong bond, strongest bond rather. So therefore these vacant orbitals, they are hybridized to form a new set of equivalent orbital. For example, this is your s orbital, this is your p orbital, this is your d orbital. So orbital like these, they will hybridize. For example, if we talk about s, 3p and 1d orbital, so it will result in the formation of sp3 d hybridized orbital, and they all will be of your same geometry and same energy. That is what they basically mean. And these orbital also have definite directional properties, which means they will be pointing, these orbital will be pointing in the direction of your incoming ligands, correct? So the okay, once you know the geometry of the complex compound, you automatically know which orbital of the metal cation or atom it is using. Okay? Alright, understanding what I'm saying? Once you know about the geometry of the complex, you will ultimately understand which orbital is going to get involved. Okay, that you'll see in the next part over here. Proceeding to the third part. Third point, bonding in metal complexes arises when a filled ligand, that I've already discussed with you, when the filled ligand orbital containing lone pair of electron overlap with the vacant hybrid orbital of metal to form a coordinate covalent bond, like that. Correct? So, magnetic moment, number of unpaired electron and coordination of a metal cation decide the hybridization and geometry of the complex. Correct? So the magnetic moment, coordination number, hybridization geometry, they all are interrelated to one another. And proceeding further, we have another point related to your strong field, weak field ligands, and that we have already discussed. Strong field have a tendency to pair up d electrons, whereas your weak field do not have the tendency to pair up electron. It is same as such. Seventh point says the bond formed between metal and strong ligands such as Cn negative CO is considered to be covalent. On the other hand, the bond formed between metal and weak ligand is considered to be ionic. Okay. Now, what they are saying that आपके जो metal और strong ligand के बीच में bond बनेगा, it is considered to be covalent. वहीं आपके जो metal और weak field ligand के बीच bond बनेगा, that is considered to be ionic. Correct. Then comes another point. The bond formed between metal and strong ligand is considered to be covalent. Same point they have been repeating. I don't understand why. Okay, let's proceed further. In octahedral complexes, the central metal cation. Okay, there comes the most important point. In octahedral complexes, the central metal cation is either D2sp3 or sp3-D2 hybridized. The d orbitals involved in D2sp3 hybridization belong to inner shell n-1d orbitals. That is why these orbitals and these complex formed by the inner shell orbitals are known as inner orbital complex. This is very important to remember. Most of the time questions are being asked, what are inner orbital complexes, what are outer orbital complexes? So you should know. You have to explain what are inner and outer orbital complexes, and you have to give an example of each of these two. Correct? So yeah, it is about inner orbital complex where your n-1 orbital is getting involved, and when your d, yes, okay, and when your nd orbital is getting involved, that is basically going to be your outer orbital complex. Correct? Then in tetrahedral complexes, the metal cation is either sp3 or sd3 hybridized, but mostly you are going to see sp3 only. So yeah, that's all about it. And in square planar complexes, the metal cation is dsp2 hybridized. P and d orbital involved in dsp2 are pxy, px and py, and dx square minus y square, leaving pz and dz square projecting above. Okay. So there they have given some information related to which orbital has been involved over here. Now comes the next point. In case of second and third transition metal complexes, d orbital involved in hybridization are inner n-1 d orbital. In case of second and third transition series as well. Okay, because the outer d orbital become too diffused to bond well. That is another point. Okay. The complexes having one or more unpaired electron, they are known as they are basically paramagnetic in nature, and the complexes having no unpaired electron, they are going to be diamagnetic in nature. Correct? So that is one thing. Okay, there comes your hybrid orbital, which are involved in the most coordinate geometries, most common coordinate geometry. If we talk about coordination number 2, hybridization is going to occur, that is sp, because one s and one p orbital is only going to involve for the bond formation, and the p orbital that is going to get involved is px. Bond angle formed in between the two is going to be okay, that is going to be 180 degree, and geometry is linear, and here they have given an example. Similarly, you can see for the rest of the coordination number as well. For example, in case of coordination number 3, we have sp2 hybridization. Orbital involved is s, px and py, and bond angle is 120 degree. Correct? And the geometry would be triangular planar, and here comes the example. So we have some example of our important coordination number 4 as well as 6 over here. So you can go through it, check wisely, and you will understand eventually what VBT postulates are all about. Sometimes they ask only postulates in your subjective paper, correct? So you need not to go through each and everything, but you need to remember the postulates very well so that you can understand it and apply it on your coming questions. Okay, we'll see the questions in your future slides, so you'll understand eventually what VBT is all about. So you have to keep remembering the postulates, only then you will able to solve the questions related to the same. So if you have any sort of queries, you can ask me in the comment section and I'll take it as soon as possible. I hope you understand that well. Thank you.